Hello and welcome to your Lecture 7 Skill Check. Today we're going to be looking at the independence test. And so here in this scenario, we're looking at a local coffee shop that sells 3 hot drinks, coffee, tea, and hot chocolate, and 3 food items, muffin, cookie, and bagel. So we're imagining that the manager of the shop selected 5 mornings at random and made a count of what was purchased by 200 randomly selected customers who purchased both a drink and a food item. So the data is shown in the table, and the manager wants to know whether there might be a certain drink and food combination that is more popular than others. And if so, she plans to offer a deal on that combination to attract more customers. So before we do anything else, let's just talk a little bit about this independence test. So in general, you are to be given counts for various combinations of 2 categorical variables. And these will appear in what we call a contingency table. So the table that we just saw is a contingency table. In contrast, a frequency table is what you would see if the test was a goodness fit test. So you're given that contingency table and you're asked whether the 2 categorical variables are associated, or to say it a different way, are dependent on each other. The counts are drawn from one population, and the null hypothesis is that the 2 categorical variables are independent. So the thing to remember here is that we have 2 categorical variables and there's a sample drawn from one population. Right, so the first question is, we're going to conduct this chi-square test, but first we need to know what the conditions are. We need to make sure those conditions are satisfied. So, just to remind you, the first condition is the obvious one: the data must be counts for categories. Here, clearly, we have counts for each pair of drink plus food category. Second, the data must be from a random sample. That's always the case for all of our statistical tests. And that's just the statistician's way of sort of maximizing the probability that we have independence. The big idea is we want to ensure that there's no systematic differences in the data in each of the counts. There's no systematic differences other than the systematic differences we're interested in. We want all other differences, in other words, all other sources of variability, to be random, so that the only systematic source of variability potentially could be the thing that we're interested in. That's the general idea of randomization. If you want to know more about that, you can take a course in experimental design, and then you can come to understand this a little bit better. The third thing, the thing that you're most likely to need to check for yourself, like say in a test or a quiz or a midterm or a final exam, is to check that the expected count within each category is 5 or more. And that's the expected count, not the observations. The observations don't matter. It's the expectations that matter. And when I say expectations, of course, you understand, I mean the expected counts under the null hypothesis. Okay, question 2. What are the hypotheses for this chi-squared independence test? Well, we are testing whether the 2 categorical variables, drink choice and food choice, are independent of each other. And so the null hypothesis is that they are independent, and the alternative is that they are not. Third question, we're going to do some calculations. We're going to get those expectations. So here's the table with the observations. What we want is to calculate the expectations. So this is the table for expectations, and you'll notice what I've done here is I've converted the marginal counts into marginal probabilities. If we just go back one, I've turned these counts in the bottom row and in the rightmost column into probabilities. And how do we do that? Well, we just take each number and divide by the grand total. And so these give the marginal probabilities. Now from Math 2208, you learn that if 2 events, A and B, are independent, then the probability that they both happen is just equal to the product of their individual probabilities. And so here, if you look here, we have the probability that a randomly selected person chooses to order a muffin is 40%, and the probability that a randomly selected person chooses a coffee is 63%. And so the probability that a muffin and coffee are chosen together under the assumption that the null hypothesis is true, in other words, under the assumption that these choices are independent of each other, the probability of getting a coffee and a muffin is just going to be the product of these two marginal probabilities. Right? So if the null hypothesis is true, the probability that someone orders a coffee and a muffin is just equal to the probability that they order a coffee, that's the marginal probability, that's 0.63, times the probability that they order a muffin, 0.4. So the expected number of people in a sample of 200 who order coffee and muffin, again assuming that the null is true, is equal to the probability that they order a coffee and a muffin multiplied by the sample size, and that gives us a product of 50.4. And so there's our first expectation. So we can go through this table and calculate all the expectations in the same way if we choose. And that's the way I was encouraging you to do it on the actual skill check. But I would like to point out that an equivalent way to come up with this expected count is to use that general formula, which is to say we take the column total times the row total divided by the grand total. In this case, the column total is 80, so we have 80 here, the row total 126, and the grand total is 200. And so just to convince you that I know what I'm talking about, if we go, let's see, if we go 80 times 126 and then divide that by 200, we get 50.4, right, the same value. Right, so we could calculate the expectations, the expected counts for each of these cells using this formula. That's probably the easiest way to do it. But again, the reason why I explain it this other way is because I want you to understand why we can use that simple formula, column total times row total over grand total. The reason why is because we're basically appealing to things we understand already about independent events. Right? Okay, so enough of that. This is what you would get if you just go in and do all those calculations. So these are our expected values. By the way, we remember the conditions. The third condition that needs to be satisfied in order to do a chi-squared test of any kind is that the expected value within each cell, all those expectations, must be at least 5. And here we can see that condition is satisfied. So we're good to go. Fourth question, determine the degrees of freedom and the critical value for our chi-squared test. So that's easy enough. Whenever you see a contingency table, the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So for this independence test, it's also true for homogeneity tests. We calculate the degrees of freedom in this way. So in this case, 3 rows minus 1 times 3 columns minus 1 gives us 4 degrees of freedom. And so we need to look at the chi-squared table. We look at 4 degrees of freedom. If we want a test at 5% level of significance, we look at that column, and we can see that our critical value is 9.488. And so that gives us our decision rule. We will reject the null hypothesis at the 5% level of significance if our test statistic is greater than 9.488. And so we can draw a picture for that. So if our test statistic falls to the right of this critical value, we will reject the null hypothesis. Next, calculate the chi-squared statistic by filling out the table. So let's have a look. Here we have our observations, and our expectations. And so in this case, what I'm going to do first is just I'm going to calculate these deviances, the difference between what is observed and what is expected. So for example, in the first case, the deviance is 51 was observed. 50.4 is what we would expect to see on average if the null is true. And so that deviance is the difference is just 0.6. So we can go through each of these 9 cells to get our 9 deviances, and you will get something like this. Yes, there it is. And so we can look through these deviances and see that some of them are quite small and some of them are relatively large. And so here's the concept behind this test again, which I like to emphasize every chance I get, because I like you to understand what the test is about. So here it is. There are differences between the observed counts and the expected counts under the null hypothesis. That's what we're seeing here. There are some differences. And the question is, can these differences be attributed to sampling variability alone? Or is there a systematic difference between what we observe and what the expectations are under the null? When I say systematic differences, in this case, I'm saying, is there evidence that some of these selections are dependent? There's some dependencies between them. Dependencies, if there were dependencies, in other words, for example, if someone, well, let me back up a second. Okay, so what do we mean by dependencies? This is always tricky. We can look at our data and we can say, well, there's a certain probability that somebody would order a coffee, right? I think if we remember back, it was a 0.63. So the probability, according to this data, that a randomly selected person orders a coffee is 0.63. However, if we already know that that person has ordered a muffin, well, there's two scenarios. The first scenario is knowing that the person ordered a muffin has no impact on the probability that they ordered a coffee. In other words, even if we know they ordered a muffin, the probability they ordered a coffee is still 0.63. In that case, these two things are independent of each other. In other words, knowing that someone ordered a muffin has no impact on the probability that they ordered a coffee. On the other hand, if we were to find that people who order muffins are more likely to also order a coffee, more likely than 0.63, then that would indicate that there is a dependency between those two choices, right? So under the null, there are no dependencies. And so we expect the differences that we observe are just due to sampling variability. But if the null is false and there are dependencies, then some of these differences are going to be accounted for by those dependencies. And that's what we're trying to figure out, whether or not there's dependencies. Right. So the other idea here is, in the end, we're going to turn these values into a test statistic, a chi-squared statistic. And if that chi-squared statistic is big, that's a measure of statistical distance between what we observe and what we expect to see under the null. If that statistical difference is big, then we're going to reject the null. If it's small enough, then we're going to fail to reject the null. That's the idea. All right, so let's check out what the statistical distance is. We can take each of these deviances. We're going to square them, each one, and then we're going to divide by the expectation. And in the end, we're going to get numbers here that represent the contribution each deviance makes to the chi-squared statistic. So I'm just going to fill these numbers in. And in the end, these numbers in this third column, each of these numbers represents the contribution of the observed deviance to the chi-squared statistic. So for example, in the first case, what was observed and what was expected under the null, they were very similar. And so the difference was small. And you can see that makes a very small contribution to the chi-squared statistic. On the other hand, we can see down here a case where this deviance is large, and as it turns out, so is its contribution to the chi-squared statistic. So this combination, this corresponds to hot chocolate plus cookie. This combination contributes the most to the chi-squared statistic, by far the most. The biggest one besides this one is 2.27. The rest are smaller than that. This is making a really big difference to the chi-squared statistic. It accounts for about half of that chi-squared value. And so what this suggests is that more people choose this combination than we would expect under the null hypothesis. If we just go back for a second and look at the table, so you can see for this combination, where is it? Here it is, cookie and hot chocolate. Under the null hypothesis, we would expect to see about 11 people ordering this combination, but what do we observe? 20 people ordered that combination. So this is suggesting that there is a dependency between these two choices. So if someone orders hot chocolate, they're more likely to order a cookie to go with it compared to, say, when they order coffee or tea. And so a dependency is suggested by this very large contribution to the chi-squared statistic. Now, of course, in the end, we still have to compare our chi-squared statistic to the critical value, and then we can make our decision. So, going to the table, we can see that our chi-squared statistic is much bigger than our critical value. So the chi-squared value, the chi-squared statistic is very far to the right of our critical value, and so that gives us reason to reject the null hypothesis. Right, so just reminding you, this is the critical value. Up here is the test statistic. Good, so we've rejected the null hypothesis, which is telling us that there are some combinations that are being chosen with at a frequency more than what you would expect if there were no dependencies. So there is evidence that there are some dependencies between these two categorical variables, the drink you choose versus the food item that you choose. Now, to end this, I just want to show you how you could use Minitab to do this same analysis. So let me just bring Minitab up for you. And let me just first show you how you would enter the data into Minitab. So you would have one column for the drink choice. And here I'm going to label what those drinks are. So there's coffee, there's tea, hot chocolates, and oh, that's it. Okay. And then on top, we're going to have columns. Each of these columns is going to be the food choice. So muffin, cookie, and bagel. And here I'll just fill in those numbers. So we have 51, 32, 43. And then 20, 11, 9. And then 80, oh, where is it? Sorry, 9, 20, and 5. So 9, 20, and 5. So I'll just double check all those numbers. Looks good, looks good. Yeah, okay, that looks right. So how do we do the analysis? We go to Stat, we pick Tables, and then we pick a chi-squared test for association. And by the way, you might have noticed if you've seen the previous video that this is the same choice you would make if you were doing a homogeneity test. So we choose that. We're going to choose summarize data in a two-way table. And now we'll pick the columns containing the data. So the columns containing the data, muffin, cookie, and bagel. And now I want to include these labels in the output. And so I'm going to pick here. You see it says rows. It says column with row labels. I'm going to pick here the column that contains row labels. And that's the first column, which I called drink. And so that's it. Once you have all this set up, you just press OK. And you can see here that we get our output. So this is the same output that is on the slide. So we can go to the slide. Right, and so see here we have our observations. And then below each observation is its expectation under the null hypothesis. So if you look back, you'll see that these are all the same as what were calculated in previous slides. On the margin, of course, you see marginal totals and the grand total. So that's how you read this table. Up here, what we're concerned with is the chi-squared statistic, 16.49. I think that's the same as what we had. Let me just have a look. 16.4895. Yeah, so that's 16.49. So that's in agreement with what we had. 4 degrees of freedom, and there is our p-value. So it's quite small. This is justifying rejecting the null hypothesis. And so again, I just want to emphasize that this particular observation, 20, versus what was expected under the null, this particular deviance made the biggest contribution to the chi-squared statistic. And so the way we can interpret that is we did reject the null mostly because this combination was so big. This deviance gave us such a big contribution to the chi-squared statistic. And so we can say there's evidence that people are ordering hot chocolate and cookie together more often than would be expected under the assumption of independence. Right. So yeah, I guess that's all I need to say. So again, the point is, the manager of this coffee shop can now say that yes, when people order hot chocolate, they're more likely to order a cookie, or you can also say if they order a cookie, they're more likely to order hot chocolate. Hot chocolate plus cookie is a preferred combination. And therefore, let's put that one on sale to encourage more people to come in to get that combination that it seems like people want. In any case, that's really all I have to say about this. So if you have any questions about anything, please just leave a question in the comment and I will address that, give you an answer as soon as possible. You can also, of course, wait till class. You can ask me then. Other than that, I guess that's all I need to say. So thank you for watching this. I do hope it was helpful, and stay tuned for more. Bye-bye.